in previous lecture we have seen the introduction about polarization, and during that discussion we came to know that the pattern or orientation of electric field in direction of propagation will tell us about the polarized pattern of the signal. It means the signal can be horizontally polarized, signal can be vertically polarized, signal can be circularly polarized, signals can be elliptically polarized. So, basically these are the three different polarizations available in RF transmission techniques to make this signal robust against the bending effect, interference effect and many other effects. Today, we will see the mechanism how can we introduce the polarization in RF signals. So, the first, if you see here how to generate circular polarization, because we want to focus on circular polarization, because circular polarization is better than the linear polarization, which is horizontal polarized or vertical polarized. So, let us start the mechanism. If you see here, there are three diagrams we have represented here. The first one is E1 is shown along y axis and x, the blue dot is showing x. So, the only vertical polarized signal is there in E1. So, it is linearly polarized. We can do it horizontally also, means the direction of propagation orthogonal or parallel will be termed as horizontally polarized or vertical polarized. If you see the second diagram, it is elliptical polarization. It is not exactly the way Lesage patterns are being generated when two orthogonal fields are introduced into the signal, and we get Lesage's pattern as exactly circular pattern in CRO. So, the third case is circular polarization. This is what we require in our dielectric resonator antennas during excitation, as we have seen in previous lecture that the circular polarization can be achieved either by modifying geometry of dielectric resonator antennas or modifying the feed or the feeding technique to DRA. So, with both techniques we can achieve circular polarization, but the outcome of the field pattern of E field will be like this. If you see here, E1 and E2 both are perpendicular to each other, and the field will rotate either in clockwise direction or in anti-clockwise direction. So, clockwise direction rotation if we are able to achieve, we will say that it is right hand circular polarization, but if we are able to rotate this E field in anti-clockwise direction, we will say LSCP or left hand circular polarization. So, we are going to see today how can we do this. The basic mechanism in feed is that either we can make E1 component dominant or we can make E2 component dominant. So, the dominant component of field will give us the rotation effect. Let us see how. Now, if we see here that the point 1 says switching from LSC to P RSCP or vice versa by reversing magnetic current by changing slot position. This is one technique. Metallic strip placed at edges is second technique. Orthogonal mode generation is another technique. Dual feed characteristics is another technique. Mode merging is also one technique. Nosed corners defining is another technique. Generating CP with single feed is really challenging task, but we have obtained this also. Keeping impedance bandwidth unchanged and getting circular polarization is very essential. DRA geometry based approach, we will see this also. So, this is how we can get circular polarization. Now, if you see, these are the fields we have drawn here using CST or HFSS, and here you see the initial fade was like this, here 1, 2 and 3. It means, if you divide this, there are 5 modes being excited into x direction. Now, after this is linear polarization plot, after we introduce circular polarized technique, now you will see this one mode, these are the 2 modes and this is third mode. So, rotation is obtained. Similarly, if you see here, these are the standstill excited modes. Now, after introduced circular polarization, you see that there is a rotation being obtained in clockwise. Similarly, here, similarly here, similarly here, similarly here. So, we are seeing E field pattern rotation. Let us see one more. If you see here, again very clear diagram is there for E field. So, this is E field diagram. These are the higher order mode excited here in this DRA. Now, after circular polarization, you feel that there is a field rotation obtained. Similarly, if you see clearly in this diagram, these are the initial fields, after rotation these are the E field patterns obtained. So, these are all circular polarized field. For better representation, if you see here one more plot, these are the mode excited and this is circular polarized fields, E fields. There is no change as far as mode is concerned, but there is a rotation being achieved in the fields. Now, what was the mechanism here? If you see here, these are the feed mechanism, this is the slot. So, it was a rectangular slot initially, later on we have converted this this slot into this. So, this is dominant, here the length of dimension of this is longer as compared to this. So, this because of higher dimensions, we are able to get the dominant field excited and we are able to achieve this field rotation, that is known as circular polarization. If you see here figure 2, the plot B represents H field inside DR without rectangular slot and C H field inside DR with stair shaped slots. So, this is stair shaped slot. Now, if we see here shape, so this is higher order mode represented here, these are the rotations with the same number of higher modes. This is known as circular polarization. If we see here, of course, these are the PDF. This diagram will give us more clarity. See, E field with rectangular slot, figure A, E field with stair shaped slot, and this is in stair shaped slot, one is made dominant. So, now the field is rotating like this. So, this is how we are able to get the circular polarization. Now, I will be able to show you few diagrams where we have created the circular polarization. Let us take this diagram only. So, if I am able to, let us take, I have drawn a rectangular DRA of this nature, and from the inner part, if we are able to extract out this material of like this, it means in this DR there is a cavity of this nature, because in place of DR, the DR material we used TMM and the TMM has 13I, it means the epsilon r is 13 or 12.8. Now, in place of that DR material, we have introduced air and the air permittivity is 1. So, we are able to get circular polarization only because of the shape of DRA. We have not altered anything as far as feed is concerned, but only the cavity of that particular shape where E field becomes dominant in one direction has been created inside a rectangular DRA, and because of that cavity created with different material, we are able to achieve circular polarization. So, likewise there are various techniques by which we are able to get circular polarization. As I already said that because of circular polarization being introduced into dielectric resonator antenna, the field becomes robust, radiating fields will be robust, because during rain attenuation, as I already gave you the example, that if it is horizontally polarized or vertically polarized, the signal gets totally 100% attenuated. But if it is a circular polarized signal, there is no effect of rain attenuation absolutely, and your signal you will be able to transmit and receive signal continuously. That is all about circular polarization. In detail we can take few cases in the next class, where we will see live dielectric resonator antennas with some sort of measurement setup in anechoic chamber, and then based on those radiation patterns we will be able to compute the change in azimuth angle, elevation angle, and then E y by E x ratio, or XL ratio is the measurement point of this. If we get XL ratio of our designed DRA lesser than 3 or lesser than 2 1, then we will say that it is circular polarized. Thank you very much.